want to go through, and thank you to CJ for reminding me where we had left off. I was just going to start at the beginning. We'll just start over. And I laugh, and then I am kind of going backtracking a little bit. But we had finished up talking about classic hypothesis testing, okay? And the idea being that with our classic hypothesis test, what we're doing is we've got a null hypothesis, an alternate hypothesis, and what we're going to go through and try and make a decision on a reject, fail to reject, based on the data and things along those lines. So here, recall that the example that we were working with, we have so we believe that there's a possibility that antioxidant supplements might reduce, possibly reverse age-related cognitive decline, right? So this is important. If we can keep older individuals' cognitive functioning sort of up and sharp, that could be a useful thing. And so what we've done is we have 25 adults aged 65 and older taking antioxidant supplements for a period of 6 months. Then we give them a neurological test for cognitive functioning at the end of that period. And with this hypothetical test, what's nice is that we know the population mean and standard deviation for individuals 65 years and older, right? And so this is nice because it lends itself to a classic Z-test because we're comparing against values that, some measurement that has a known population mean and known population standard deviation. And then what we've said here is based on previous psychometric research, we're saying a change or difference score exceeding 10 or more points has practical relevance. Now, Chris last time brought up and had some questions about sort of this 10 or more point difference, noticing that this was about a half a standard deviation. That's a good point. This is something I just kind of made up for the purposes of references here. But again, we can run into situations where this is the normal variability, but in certain types of measurements, we can say there's some practical or meaningful difference, so that's maybe less than a standard deviation. And so that's kind of the anchor we're using here. Okay. So again, first, what we're going to do with the classic approach, we're going to state the null, or state our hypotheses. Our null hypotheses, we're basically saying there's a zero association, there's a zero difference. Almost always what we're doing with our null hypotheses, if we say we've got a statistically significant effect, almost always it just means that some value, we don't have sufficient evidence to claim something is different than zero. Okay? Our alternative hypotheses, this is sort of depending on whether we have a directional or non-directional hypotheses, this is saying that the difference between the two is not zero, or the manipulation has some effect, or the association isn't exactly zero, something along those lines. But remember, this is going to come into play when we're talking about some limitations of this whole procedure, is our traditional test only tests the null hypotheses. This is the only hypotheses that we're actually sort of looking at. What ends up happening is if we reject the null hypotheses, we're taking that as indirect evidence that the population from which we've drawn this sample has a mean or some value that's not equal to sort of whatever the reference is. We're not testing that exactly. We're not looking at or testing the alternative hypotheses. It's all about the null hypotheses, hence null hypothesis significance testing. Okay. Talk about statistical models. And talking about, in general, our statistical model just refers to a set of assumptions about how data have occurred, right? With our one sample test, my statistical model is that what I'm seeing is a mean value of scores that was generated from a population having some certain mean, right? That's my assumption. And so for what we're generally working at from a statistical standpoint with our calculations, we're almost always focused just on sort of whatever the point estimate of the null hypothesis is. But in reality, this whole statistical endeavor, the whole mathematical theory is predicated on a number of other things happening, right? There are implicit assumptions that our sample is representative, that our sample is random, that our distribution of sample means is normal, that we have a correctly specified model, right? This is saying that for these analyses, everything that should be in there needs to be in there, and everything that's not important isn't, right? And this starts to become tricky, particularly with a simple test like a single sample t-test. We've only got one thing that we're measuring, right? I don't know of any psychological phenomenon that's been dependent on only one thing, right? And so we've got to be, our statistical models And so this starts to become relevant as you get farther on into like SEM types of analyses, where statistical models are a representation of reality. They're not exactly reality, right? We spend a lot of time in SEM stuff talking about what the correct model is or what the population model is. The correct model is probably too complex to even sort of measure reasonably within the context of our stuff, right? What we're trying to do is come up with a parsimonious representation that does a reasonable job of sort of capturing whatever the phenomenon of interest is, right? So for example, if I have, we'll talk about this when we get into regression stuff next semester. If I've got data that looks something like that, right? What might I hypothesize is an appropriate model for that type of relationship? What do you think, Tamara? What's up?
A linear relationship.
Okay, yeah, I could have a linear relationship, right? And so that's probably what I'm going to do is I'm going to say, all right, well, it looks like that's maybe my relation, right? What else do we see there that might be going on? I might have a curvilinear function, right? And so what I might find is that in actual fact, sort of this model, something that has that might actually fit a little bit better, right? But from a statistical standpoint, so I've got two competing models. My first model is that there's a linear relation between x and y. My second model is that there's a nonlinear or curvilinear relation between x and y. These are two competing models, right? These are two competing theories on what's given rise to the data that we've observed. Now, which one of these models is more parsimonious, the linear or the curvilinear? The linear, right? And so when I'm looking at this, what I might say is like, yes, in these specific data that I've captured, it looks like I could fit a curvilinear model. That might be a little bit better, but it's also added complexity. Is the added complexity of the model worth sort of the additional fit or representation, right? And so if I find that my linear model, R squared for my linear model accounts for 70% of the variability in the data, and my nonlinear model accounts for 71.5%, I might just say, I'm just going to go with the linear, right? Because it's more parsimonious and it captures, so the added benefit I get with the nonlinear model is just a little bit more, right? Now, if I'm going through and there's other things going on in the model that I haven't specified, things that are important that I haven't included, then I run the risk of having a model that's not well specified. I've got a misspecified model, and what this means is I've observed a relation between two things, but the association that I'm seeing may not actually be real in the population, right? So if I see, let's say I find a correlation between blood pressure and income, okay? I find that as people's blood pressure increases, their income increases, right? And that would be kind of a snazzy thing to say, right? Like, oh, I can say, well, as sort of type A people, as their blood pressure sort of increases, then they're going through and they're sort of earning more money or things like that, right? And that's kind of a sexy thing I could throw out to the TV and they'd probably catch it and I get super excited about it, right? And in my data, I might find that yes, there is a correlation between blood pressure and income. What else could be going on?
Lots of stuff.
Lots of stuff, yeah. What happens to our blood pressure as we get older? It increases. What happens to our income as we get older? It increases, right? And so in my model, I've said, here's this population, I've estimated a population relation, a population association between blood pressure and income, right? And I've said, oh, this is a real thing. But in actual fact, probably what I've done is just captured a natural correlation between I'm just getting older, more money as I get older. And so that actually the population correlation between income and blood pressure could be zero once we account for things that need to be in that model, right? And so this is where we start needing to think about when we're evaluating research, is the stuff that needs to be in this model, Have we included the components? And this is where it starts to become incumbent on you all to have expertise in your sort of area of investigation and know what types of things we should include. This is something I struggle with, sort of trauma-related stuff, right? We have good meta-analyses. These are all the things that are associated with sort of PTSD, PTSD symptom levels, right? But rarely do we have social support and age and trauma severity and childhood adversity and like all these things that we know are associated with the outcome aren't included in our models, right? I just happened to pick emotion regulation or something like that because it was cool and I had access to it, right? When in fact, you make a strong argument that that model's not specified because, not properly specified because there's a bunch of other stuff that needs to go in there. You know, we gotta weigh this out. We can't have all the variables in the world in our models. But this is where sort of thinking carefully about what we're doing and how this all fits together starts to become important in critically evaluating research. Okay? So, talked a little bit about our models here. And so for a supplement example, our null hypothesis is mean cognitive functioning. Our supplement among population of older adults taking supplements is equal to 80. Alternative hypothesis is that the mean cognitive functioning in population of older adults taking herbal supplements is not equal to 80. When we're stating our hypotheses, are we ever concerned about the sample? Nope, I don't care about the sample. Sample is a means to an end. I've collected a sample as a way to try and get an idea of what this parameter looks like in the population, right? So making sure when we're stating our hypotheses that we're stating those in terms of population-based parameters. Then what we need to do is we need to go through and set our decision criteria. Within null hypothesis testing, sort of the whole process is to say, assuming that the null hypothesis is true, assuming that this the population for which the sample has been drawn, assuming that it has some mean value equal to whatever the reference value is, what's the likelihood of obtaining a sample with these characteristics or more extreme, right? And so in the case where I find the sample mean to be much different than sort of whatever my null value is, we interpret this as evidence that the data is incompatible either with the null hypothesis or some other assumption of the underlying model. The thing to remember here is if we reject the null hypothesis, it doesn't tell us which one of these things is going wrong, right? So if I, in this study, if I end up rejecting the null hypothesis and find that my sample of older adults taking antioxidants, their mean cognitive functioning deviates from that point, reference point of 80 to a degree that I would say these data are unlikely to be consistent with the null hypotheses and the underlying assumptions. That might mean that the population of older adults taking supplements, it might mean that they do have a different mean cognitive score than 80, or the assumptions of my underlying model are all wacky, right? And this involves data assumptions, methodology assumptions, and things along those lines, right? Maybe I just went through and I pulled a convenient sample of older adults who were sort of interested in sort of crossword puzzles, sort of things, sort of staying active and things like that, and they come in, maybe these are people with, similar to Allison's talk, right? They're like, oh, I have perceptions about sort of what my cognitive functioning is, so I want to be in this study. And then I do find that they've got a different value than a bunch of other people. Well, maybe it's because there actually is sort of a difference, or maybe it's just because something that's going on with my methodology and things along those lines. The thing is that our hypothesis test won't tell us which one of these things it is. It just says these data appear to be inconsistent with the null hypothesis and all the auxiliary assumptions that go along with it. It's up to us to go through and evaluate which of those things is true. On the other hand, if I get sample means that are similar to my hypothesized population mean, then we just say that these data are compatible or not necessarily surprising, assuming the null hypothesis in the underlying model. The thing to remember here is people sometimes interpret p-values as evidence for my null or for my alternate hypothesis, or evidence that my alternative hypothesis is true. For a lot of this stuff, we don't have a real good alternative hypothesis. Our alternative hypothesis is just that sort of my population mean is not equal to something, right? That's basically infinity minus one possibilities for whatever this thing is, right? So it doesn't tell me, it doesn't directly provide evidence for my specific theory. And so what we determine, so we use to determine the set point for whether or not we find these data to be compatible and incompatible is going to be determined by us, our alpha level. This is going to set our critical regions to where we're saying at this threshold, with traditional hypothesis testing, at this point, we've got something that is either sort of exceeds what we would expect or is about consistent with what we would expect to be true. Okay? So for our supplement example here, this is our distribution of sample means, assuming that we have a population mean functioning that equal to 80. And what we're going to do is we're going to set our alpha level equal to 0.05. And we just do what we're told to do, and this is convention. This is kind of our set benchmarks for how we're going through and doing things. Okay. Then we'll go through in our calculator statistics. For our Z criteria, or for our Z tests, we have a reference population with a known mean and standard deviation. We plug those in, calculate a confidence interval around the point estimate based on our sample data. We can also go through and calculate our test statistics. This is our Z-score. This is going to be our observed data minus our reference value under the null divided by our standard error. Again, wanting you guys to think about sort of what's going on, so what's actually happening within this statistic. Numerator here is the discrepancy we've gotten between what we've observed and what we're assuming under the null hypotheses. The denominator, your standard error here, is indicating how much difference you would expect if the null hypotheses were true. How much would you expect that mean estimate to jump around based on replications of a sample of a certain size? Okay, so a couple examples here. Scenario one, we want to look at the Z statistic of individuals taking antioxidant supplements, scored an average of 92 points on the neurological exam, assuming population values of mean of 80 and standard deviation of 20. And then in scenario two, if we observe a score of 80 points on this examination. So here, supplement sort of scenario one, we've observed in our data that this sample of, what is it, 25 older adults came in registered a cognitive functioning score of 92. Okay, so our alpha level is 0.05. Critical values, and we get these from our Z table, right? Plus or minus 1.96. This marks off that upper 2.5% of the distribution, bottom 2.5% of the distribution. Got those right here. My mean is 92. I calculate my confidence interval. I'm going to get a confidence interval of 84.2 to 99.8. Thoughts on that confidence interval? What do you think, CJ? Are we super excited about that confidence interval?
No.
Why not?
It varies a decent amount from mean.
And why does that make you not super happy?
Makes it tough to, well, it makes it tough to be confident about our mean.
Yeah, yeah. So in terms of thinking about practical differences, right, and sort of whether or not things are meaningful, this 95% confidence interval says that mean values in the population of older adults taking antioxidants, values as low, amount of values of mean cognitive functioning as low as 84.2 to as high as 99.8 would be sort of would be compatible given the data that we've collected. Given the data that we've collected, anything within this range is fair game, right? But if I look at the bottom end, so what's my reference value that I'm testing against? 80. So anywhere from about 4 points over could be meaningful, right? I've got a 12-point difference that I've observed. But anything as low as 4 points could be sort of reasonable given the data that I've collected, right? And so I might be less excited about a 4-point difference than a 92-point difference, or sort of a 4-point difference than a 12-point difference. Now, at the end of the day, what's my best guess for the actual population difference? Yeah, 12 points to the mean, right? That's still my best guess. But if you were to say the actual difference is only, say, 4 points, I shouldn't be surprised given the data that I've collected. Or if you would say it's 20 points, wouldn't be be super surprised, right? So wanting to think about what the sort of width of our confidence interval is starting to tell us about the question at hand. But if I go through and I calculate a p-value, it's sort of easy peasy for sort of punching in these p-values for a bunch of different statistics. Gives me a p-value of 0.003. My test statistic, my z-value here, get a value of 3. This is clearly within beyond sort of my cut point, within my critical region here. And so what I would do in this scenario traditionally would come to a decision where I decided to reject the null hypothesis, right? And I would say that these data appear to be unlikely, assuming that the null hypotheses and all auxiliary assumptions are true. Okay? This is saying that if the population of older adults taking antioxidant supplements really is 80, it would be very, very unlikely for me to have gotten this sample that I've gotten, assuming that it's random, assuming that it's representative, assuming we took all those other things. Scenario 2, a little bit different. Here we've observed a value of 84. My alpha level is still 0.05, critical value is still plus or minus 1.96. Here, the width of the interval is the same because we haven't changed anything, we just changed the point estimate, right? So here, we have a lower bound estimate of 76.2 to an upper bound estimate of 91.8. Again, Chris, what am I, back row Chris here, what am I thinking about? We start calling BC.
It's probably unlikely that it's too different from the actual, or the observed mean of 80, because that mean is included in the confidence interval.
Okay, yeah. And you're exactly right. What mean is included in the confidence interval?
The one that, the population mean?
Yeah, so 80 falls within that interval estimate, right? So that suggests, this interval estimate suggests that a population value of 80 is reasonable given the data that we collected. It's not incompatible with the data that we've observed, right? And we're going to be careful about this because one of the things we do, we talk a lot about interval estimation and sort of why this is preferable. The one thing we don't want to do is fall into the trap of turning our interval estimation into just a hypothesis test, identifying whether or not that point estimate or the null estimate is in the interval, and then just saying it's significant or not significant, right? Because basically what we're doing is then eliminating all the good stuff that we get with our interval estimates and sort of just making yes or no decisions. But you're exactly right. But if I was looking at this, I would say, well, based on the data that I'm seeing here, we could see sort of a difference in between my population of older adults taking antioxidants and sort of the general population, anywhere from my antioxidant population scoring close to 12 points higher, which would be pretty big, right? All the way down to scoring about 4 points lower than the general population. So at the end of the day, what am I left with based on what can I conclude from these data? What do you think?
Very little.
Very little, exactly right. I don't know, it's just inconclusive. Like, I mean, if you said, yeah, there's a big difference between these two populations, okay, I mean, that's possible. You say, well, it's actually an incremental decrease. Okay, that's possible too. Remember, if we're talking about a 10-point difference, right, even if it does end up being 4 points lower in terms of absolute difference in the population, if I'm saying a 10-point difference is the minimum of what's sort of meaningful, basically I'm saying, well, there's anywhere from no difference, no sort of functionally meaningful difference, all the way to something that may be a little bit higher, right? So it's just incredibly inconclusive. We don't know and can't conclude a whole lot from this. Here, our Z statistic is falling within the body of our distribution, and so we should probably conclude that the data that we've observed is not inconsistent or incompatible with our proposed null value of having a population value of 80 within the population of older adults taking supplements. All right, so one and two-tailed tests. I want to touch on this real quick. Two-tailed tests is what we've done here. These are non-directional tests, right? And this is typically what we do is even if we sort of have hypotheses, we should have hypotheses on so which direction our results are going to fall. We will typically almost always analyze these as a non-directional test where we're going to place half the critical region in the upper end of the distribution, other half in the lower end of the distribution, right? And so what we end up doing when we're identifying critical values, we take that alpha value divided by 2 to identify where those cut points are. Okay? But then once we do, if we were to look in our Z table, if someone tell me, someone have a Z table? Chris, you have it? Oh, that's a T. Someone have a Z?
Wait, no, wait. Okay.
You got it?
No,
I have it.
wait. Come on.
You got it.
Now she can go. Wait, no. Files.
Files, you get in there.
See, that's another thing.
You can have the next one. All right.
Ah.
Tomorrow, tell me what's the probability value in the tail associated with Z equals 3? Go for it.
2%?
2%. What's the actual decimal place?
0.0013.
0.0013. 0013. Okay. So if you look at your Z table for a critical Z of 3, if you look at the probability of obtaining a score of 3 or a Z score of 3 or higher, probability in that tail is 0.0013, right? You'll notice that our p-value here for our two-tailed test is 0.003, right? Where did this come from? What did we have to do to the probability value that is in the table? Multiplied it by 2, right? So if you take 0.0013 and multiply that by 2, you get 0.0026. That's your p-value there. Because what we've done is we've said, okay, what we would do if we were to find actually in this study that supplement use looked like it was associated with considerable decreases in cognitive functioning, we would still identify and interpret that as well, right? And so from a probability standpoint, what we're doing is we're saying, okay, well, with our non-directional test, we found this, but we would also talk about this if we were to have found that. And so we're taking that probability statement and probability function and multiply it by 2. Same thing here. What's the probability of in the tail for a Z equal to 1?
Good for it. 62.
What's that?
62%.
0.062?
I don't know. I'm just doing that. I just multiply the p-value by 2.
You just, I don't know table. I'm just throwing out numbers. Yeah. Tell me exactly what's the value, exact value for 1? What's the value of 1?
1587.
0.158.
Oh yeah, I divided by 2.
7. Yep. And then take that, multiply that by 2. 0.317. So again, we're just getting that. And this can be kind of a tricky sort of thing. So just wanted to make sure that we're clear on this. Okay. Now, sometimes what we can do, and we'll talk about this, and this is controversial, is we can run one-tailed tests. Okay. If I have a directional hypothesis, and I say that my expectation is that supplement use is going to be associated with an increase in cognitive functioning. And if it's associated decrease with cognitive functioning, I don't care about that. It could result in a 20-point reduction, but at the end of the day, that means nothing to me. I don't care. What I can do is choose to do a one-tailed test. With a directional null, our critical region, the whole thing is put in the upper tail or the lower tail of the distribution. If I find anything that's complete opposite what I would expect, that's still a null result. I would be able to reject a null hypothesis. Doesn't matter if cognitive functioning is 0, right? Now what this does is it reduces my critical threshold because I put all my eggs in one basket, right? And so this is controversial because what it ends up doing, if I'm running one-tailed tests, is it functionally lowers the threshold for me to claim statistical significance relative to sort of if I'm running a two-tailed test, right? So there are cases where people will advocate for the use of one-tailed tests. If you try and use one-tailed tests in research, you'll often get dinged because people will accuse you of just trying to reduce the threshold, particularly if you've got a bunch of stuff that would be not meet traditional threshold for statistical significance, and then you just claim that you decided a priori to run one-tailed tests. That's probably not going to be well received. there are legitimate arguments for using one-tailed tests. The thing that gets a little bit confusing though is how do we calculate our confidence intervals, right? We're calculating the confidence interval for a directional test. What we end up doing, because we're putting all of our critical region into one table. So we've got our alpha is 0.05, and so I want 5% of the distribution to be in the one tail. I have to adjust my confidence level, because otherwise, if I am running a one-tailed test and I run a 95% confidence interval, so the stuff at the high end is not going to match up with what I'm testing and things along those lines. And so for a directional test, if I have alpha equal 0.05, what I'm actually going to do is calculate a 90% confidence interval, and that way my upper bound estimate, if I'm expecting sort of cognitive function to be higher, my upper bound estimate is going to, or my lower bound estimate is going to correspond with sort of what I'm actually looking for within that text, Okay. So here with the one-tailed test, again, we're back to scenario one where I've got a mean value of 92 that I've observed, alpha level is 0.05, but now my critical value is 0.165. Why is this silent?
Is it because of the are we seeing the same scenarios?
Mhm.
Okay, sorry. Just wanted to make sure. Okay, it's because of the 85.4,
The what?
the confidence intervals?
Okay, yeah. So it's confidence interval, but my critical value is, before it was plus or minus 1.96, and now it's 1.65. Why is this so low? I move my critical region. So if I go through and I look at, in my Z table, the probability in the tail associated with a value of 1.65, I'm going to see that it's about 5%. So this is the marking, this is the Z-score that marks 5% of the distribution just in one tail, right? But what you can see happens here, now before my critical value was 1.96, now it's only 1.65. It's decreased sort of the threshold at which I'm going to claim statistical significance for using traditional testing. Okay? But we'll see that our interval estimate here is also shrunk a little bit because we're using a 95% interval estimate, and so now my lower bound, right? Chris, see if I was using this and wanting to see has my null value fallen within sort of that region, we'll see that this is actually sort of the lower bound for what I would expect given my sort of one-tailed test. Same thing here, if under the scenario 2 where I've got a mean of 84, alpha level 0.05, and my critical value is here 1.65, because I'm assuming that supplement use was going to increase cognitive functioning. So I put it all in the upper tail. My mean now is 84. Here's my 90% confidence interval. That's putting actually 5% in one tail, 5% in the other tail, but I'm only interested in one tail. So we see some change in my interval estimate here. Also notice that my p-value changes, right? Before it was 0.003. Now, Z3, now I'm just worried about the one tail, so I'm not multiplying that p-value. It's just, this is the probability of me obtaining a score of 3 or higher, period. Anything that happens down here, I don't care about it. Questions about one and two-tailed tests? Yeah.
So you were mentioning earlier that you suspect like a directional relationship. You can use a one-tailed sometimes in specific scenarios, but what if you find the complete opposite of what you were expecting?
Yeah.
How would you go about reporting that?
Technically, you cannot report that.
Right.
Because if you use the one-tailed test, that is not, there's no possibility that anything that far below would even be meaningful or relevant to anything that you would ever do, okay? So what you would do is you would, it's in the opposite direction, you get a negative test statistic that's sort of super far in the opposite direction, you would fail to reject the null hypothesis, and that would be it. Because if you start talking about it, you're like, oh, I used a one-tailed test, but wait a minute, this is actually going the other. You can't have your cake and eat it too, right? And this is why it starts to get difficult to justify a one-tailed test. because it's hard to think about a situation where even if something happened to fall in the extreme opposite direction, that we wouldn't think about that as important or meaningful or interesting for some reason. I'm having a hard time thinking about an example where, so I'm expecting sort of this mean to be higher than the reference population, but if I actually find out it's considerably lower, that's inconsequential and doesn't mean anything for the purposes of our study. I mean, it's kind of hard to come up with sort of an example of that, right? And so that's what you for sure get super named if you say, oh, I'm going to do all my one-tailed tests and then start. Now, one possibility would be that if I were to find, sort of based on the history, sort of all sort of possible evidence and things along those lines, that there's no reasonable explanation for me to find an effect that's in the opposite direction. Everything we know in this area, if I find something in the opposite direction, it means something's fundamentally wrong with my study. That it's just impossible for this to happen, right? Then maybe I can make an argument for, we have so much evidence that suggests this thing causes impact in this direction that a two-tailed test doesn't make any sense. If I do find something in the opposite direction, it means my study screwed up and I'm not even trying to publish it because I got serious methodological issues. Maybe they need to go through it and make an argument for that, right? But it starts to get difficult. But you'll start to see, like, you know, if I have a small sample, if I'm worried about type 2 error, right? Failing to detect an effect that is there and is meaningful, and I've got a minimum sample because it's just next to impossible to get people to go through and do this. You know, you might be able to make an argument for one-tailed tests if you have a strong theoretical basis for predicting that, a strong evidential background for predicting that, and just what you've done is really novel and really cool. It's just that no reasonable person could expect you to have a sample of 500 people. You might be able to sort of make an argument for that. It just starts to get difficult because what people are going to assume is that you're just trying to got your finger on the scale, that you're trying to sort of make claims that you couldn't do if you're using a two-tailed test. Questions on this? All right, so going through runner test, calculated all our statistics. What we need to do now is draw some sort of conclusion. And so if we're doing this well, we should be drawing some substantive conclusion about the range of possible values, right? So I find that, sort of here's my lower end estimate, population estimate that would be compatible with the data. Here's the upper end that would be compatible with the data, saying something about that, saying something about the width of that interval, the precision of my estimate, which is associated with the width, effect size, size of effect based on my interval estimates, things along these lines. We'll talk about confidence interval, or excuse me, effect size a little bit later. My decisions from a traditional approach to null hypothesis significance testing, I can reject my null hypotheses. If I reject the null, this is typically what I do when my test statistic falls in that critical region, right? What this suggests, and sort of the interpretation of this, and it starts to get important that we get technical with this, suggests that our sample data are unlikely, assuming that the null is true, and all corresponding assumptions in my statistical model are true. Now, if I reject the null, just rejecting the null doesn't tell me which one of these is. It might mean that sort of the population from which I've drawn the sample is very unlikely to have a value equal to sort of my reference mean, or it could mean I've just done a terrible job and I've violated all my assumptions and I just cherry pick people with higher values like I would expect. I don't know. My test statistic doesn't tell me that. I have to go through and think carefully about the study to sort of draw that conclusion. But if I reject the null hypotheses, my indirect conclusion is that the sample from which this population was drawn likely has some mean that's different than specified under the null hypotheses. Right? My data say the population from which I pulled this sample is very unlikely to have this mean. As a consequence, it probably has some different meaning than sort of what I had specified. Okay? And so this is our indirect support for our alternate hypotheses. On the other hand, if my test statistic falls within the body of the distribution, I'm going to fail to reject the null hypotheses. I'm going to say, it looks like these sample data are at least plausible based on assuming that the null hypothesis is true. Assuming that my population of interest actually does have a mean value equal to sort of the null. The importance here is that we always conclude that if we fail to reject a null, conclude that we have insufficient evidence to claim an effect. This is agnostic versus atheist. We're not saying there is no effect. We do this all the time. Just had a conversation with one of my friends who's reviewing papers, a neuropsych guy, and sort of asking some methodological stuff. And said he had, sample size, cell size of like 30, and they didn't find differences, and so they said there's no differences between these groups. That's not what that says. We can't conclude that. We can say we don't have enough evidence to say conclude that to make a strong argument that there is a difference. This is what I'll do. I'd say sort of based on these analyses, it looks like these groups were relatively comparable, right? But what we can't say is that there's no difference. That failure to reject doesn't say that there isn't, that these two population values are identical to one another. It just that we don't have enough evidence to make a strong argument that they are different, okay? And so this is very, very different than saying that there's no difference. We're not saying that there's no difference. We're just saying we don't have enough evidence to say that there is. It starts to become important in sort of thinking about carefully claims and things along those lines, right? So as we go through this class and hopefully in your research, being careful about how we're interpreting that fail to reject. Questions about this? All right. So again, failing to reject doesn't prove that there is no effect. It absolutely doesn't. We should never be predicting the null because in order to pull strong evidence for an actual null effect is quite difficult. Wilkinson never used the unfortunate phrase accept the null. We don't accept the null. We just fail to reject the null and say data are inconclusive. Chris, in terms of interpreting the bounds of that confidence interval in scenario 2, right? We could have anywhere from our population could have a 4-point decrease, or it could have a 10-point increase. It's just not super informative. I don't know. I can't draw any strong conclusions about sort of this effect based on the data that I've had. This is essentially what we're doing in the fail to reject. Tara made me credit her for this. Cite my wife for this. All right. Conclusions. All right. So we're gonna try to take these recommendations and try and incorporate this in a way. It's hard sometimes, particularly if you haven't been doing this for a long time, to start to think about how do I go through and take all this stuff and put it into something that means something that communicates information, right? So I'm going through, if I'm getting things out at the last minute, it's because I'm trying to go through and figure out ways to discuss or give you language to go through and talk about this in ways that don't fall into common traps that perpetuate problems with null hypotheses testing and things along these lines, okay? So for our first conclusion here, based on the information that we've pulled together, we could say point estimate mean cognitive functioning in older adult 10-key antioxidant supplements was 92. What I've done here is I've told you sort of what my point estimate is. So this is the estimate that I found in terms of sort of our best guess for the population value. Data in the study suggests scores ranging from 84.2 to 99.8, reasonable upper and lower bound estimates of cognitive functioning in a larger population. Again, I'm being very specific. I'm telling you this is a population estimate, right? Now, it feels weird to, with a sample of 25, be talking about population estimates, but that's what the whole process is about, right? This is our best guess. Probability of randomly selecting a sample of 25 with average function 92 or greater, blah, blah, blah. So this is just giving you probability values. Test falls within the critical region. Assuming no meaningful violations of assumptions of the underlying statistical model, conventional decision rules recommend the rejection of null hypotheses, right? And then here, this is sort of starting to pull in sort of more additional information. We say, important to note that estimates supported by these data are compatible with meaningful effects in the elevation of functioning. So our upper limit is 99.8 relative to the general population of adults, as low as what lower bound estimates falling below the threshold of the practical effect. effects, right? So our lower bound here is 84.2. We're saying so we need to have a difference of 10 points or more in order to claim a meaningful effect. My data are also consistent with a difference that would be actually not functionally meaningful in terms of what we're trying to do. So whereas these data offer support for higher assessment scores in older adults reporting regular antioxidant use, additional data needed to determine the extent to which elevations are consistent with meaningful effects. Okay? So this is me trying to go through and pull in. And so one of our big criticisms is of using null hypothesis testing is we just say, as long as it's statistically significant, as long as we reject the null hypotheses, then so it's inferred that it's a meaningful or important effect. Actually, with these data, and so again, and we're going to talk about p-values as interpreting p-values as a continuous index of compatibility of the data with the null hypotheses. These data are not compatible with the null, right? It says that sort of the population cognitive functioning in older adults taking antioxidants is probably not as just not a plausible estimate based on the data that we've got. But if we take a look at the lower bound estimate, it also suggests that it's possible that even though you see elevations, it might not be elevation to the extent that it's something that's going to be meaningful in terms of practical effect for assessment functioning and things along those lines, right? What could I do with this study to get a more precise estimate of the possible true impact of supplement use on cognitive functioning? What do you think, Nick?
I guess you could use a different measure of cognitive functioning.
Could you use
and
a different
also-
measure?
Maybe also start comparing to a group that isn't taking antioxidants to see what their
Actually do a
cognitive
mean
function
face
is.
comparison, yeah. From a methodological standpoint, so just from a straight statistical standpoint, what could I do to increase the precision of my estimates?
Increase sample size.
Yeah, right. Because my point estimate, 92, is consistent. My best guess is that I'm seeing a meaningful effect, right? A meaningful practical difference. Not just it's not zero, it's actually something that's potentially meaningful. But I only got 25 people in my sample. So my interval estimate, as CJ pointed out, is quite large, right? It's anywhere from a trivial increase to something that's a very, very serious increase, right? And so what I might do here in terms of thinking about sort of what we could do to improve on this and improve our inferences, instead of having a sample of 25, have a sample of 100, and then see what that does, if that shrinks things down, right? So wanting to, even though within the context of these data, we definitely would say that we very clearly reject the null. We would call these statistically significant results. But in terms of practical impact, wanting to qualify that with, well, there's still some stuff we're not clear on. Conclusion 2 for scenario 2, we've got older adults sort of mean value here that we've got relative to general population, however plausible estimates of functioning, and the target population based on these data range from 76.2 to 91.8. The probability stuff, we're actually going to do a whole lot with that. So we say decision rules would say we would fail to reject the null, say although data are compatible with estimates suggesting meaningful elevations in function. Right? We're acknowledging that even though we have failed to reject the null hypothesis, our data are plausible with maybe it does, right? Upper ends suggest that maybe that we could be seeing, if you told me that there were meaningful elevations in functioning associated with supplement use based on these data, I would say possible, certainly. But we would say at best inconclusive with respect to statistical and practical benefits. We just don't know. And again, this is going to be something where we're going to start looking at the methods. Again, my best guess is that it looks like this is maybe a trivial increase in functioning associated with supplement use, but I don't know. It's tough for me to draw strong conclusions about the data based on the data that I'm seeing here. Questions about how I've gone through and structured and framed this. And again, so when you all are working through, please don't, okay, so all eyes look at me straight in the eyes right now. Chris, straight in the eyes. Please, please, please don't take this as like a template and then copy and paste and plug in things like that. Technically, that's plagiarism. I'll get upset. Like, so what'll happen is first I'll read it and I'm like, that's beautiful. That's, so they can't read your eloquence at which you sort of like this, and then they'll click on me like, ah, shit, that's what I had written with just new values plugged in. Don't do that. But what I want you to do is going through and trying to provide you with a structure on examples of how to talk about this and how to pull in different pieces and components. One of the things we talk about this in terms of best practice approaches to statistical analyses is talk about pulling in other things that start to contribute to and sort of provide more context for what we're seeing and what we're not seeing. But as we start to add other things in, it starts to get harder to think about, okay, how do I get this together in something that makes sense? I'm going to do my level best to try and provide you with examples of sort of how you might go through and interpret things. So do go through and take a look at those to try and see sort of how you might work those in, and so then use kind of your own stuff to go through. And again, play around with it. This is something I'm really looking for in terms of giving people extra bumps on points and things like that, is to the extent that you can sort of use some of these different interpretations of confidence intervals and effect sizes and things flexibly. That's just demonstrating that you have a strong understanding of the conceptual interpretations, even though from a practical standpoint it is easier to just sort of, I've got my sort of plug and play tech language and I just kind of plug that in there. So just to keep an eye on that stuff. Okay. Questions about interpretations on either one of these examples for us. So this was just covering our traditional null hypothesis testing. Let's do this. Let's take a break and come back and we'll jump into all the reasons everything we know is wrong. So. Thank you for hanging with me. I know a lot of this stuff has been sort of repeat kind of information that you're probably already familiar with, but just it starts becoming really, really important to know the nuts and bolts before we get into the next stuff. So any questions before we jump into new information? Okay, cool. So real quick, type 1 error. This is an error that makes when we reject the null hypothesis when the null hypothesis is true. We say that we have an effect or an association in the population when there isn't one. Historically, we've identified this sort of a classical approach. We identify this as a sort of just a fluke random accident, right? If here is the distribution of sample means that I could get, right? And I get one out here when actually sort of the mean value is here, we would say, whoops, I made a type 1 error. I just had a 1 in 1,000 chance and I sort of got something that was too extreme. I've claimed an effect when there isn't one. I just happen to get an extreme sample out here. So what we do to avoid our type 1 errors determined by our alpha level. Again, assuming what, so notice an asterisk this here, and this is one of the common misconceptions of interpreting your p-value, sort of identifying sort of this is the probability of obtaining a sample of this extremity or more due to chance. Well, we know that it's not just due to chance. There's a whole lot of systematic methodological issues that also can contribute us to getting extreme samples, right? So that's actually not an accurate interpretation of your p-value. But from a classical sense, assuming from a mathematical standpoint that we've conducted mathematically pure and perfect studies that have no flaws, that have not violated any assumptions, what we would say is our alpha level tells us what level at which we're willing to make these types of type 1 errors. If I set alpha at 0.05, we're going to reject with the probability of obtaining the data, assuming all null and auxiliary hypotheses is less than 5%. So less than 5% of the time will I identify a test statistic that falls sort of in the extremes when in actual fact I should be getting something and rejecting the null, or fail to reject the null. Alpha 0.01, 1 in 100 chance that I'm going to sort of get this, assuming the null hypotheses and all auxiliary hypotheses are accurate. So setting our threshold for our type 1 error, 1.96 corresponds in terms of our Z-table, 0.05, we've been working with this, 2.58 to alpha 0.1, 3.29 to our Z-score, alpha equals 0.001. This will start to become relevant, typically is sort of this threshold, and later on when we're working in screening for regression and identifying sort of how large does our z-value have to be before we start saying, this is probably not something that qualifies as an extreme value or something along those lines. So these are just good values to keep in your head. So this is our type 1 error. So we manage our type 1 error from classic sense using our alpha level. Type 2 error, this is when we fail to reject the null hypothesis when the null hypothesis is really false, right? I'm saying I don't have evidence for an effect or an association when there actually is one out there to be found, and power is the issue that we're typically concerned about here, right? I'm working with, and I've got my sample of 30, and I fail to reject the null hypothesis, and I say I don't have evidence of an effect or a relationship, when in actual fact there's something sort of there that's potentially important that I missed because I don't have, I've made a type 2 error. Okay? This is probably far and away the bigger problem and far more common error that we make within psychological statistics or behavioral science. This is particularly likely if I've had some sort of treatment or manipulation. I'm doing something, sort of CJ, you're running a manipulation in your lab, and it has a meaningful effect. It's just a small effect. You don't have super big samples. Maybe your measurements are a little shaky or not so great, or have a lot of fuzz in them. All of these types of things can start to lead to type 2 errors, right? Again, pulling in sort of methodological aspects and points doesn't sort of fit together in words. This is why it starts to become important to be making sure that our protocols are tight, that our measurements are good, that we've pulled out all possible sort of fuzz and things like that that could start to impact error in our samples, so that we have the best chance to detect our effects. So this will probably look familiar. I have no effect, the null hypothesis is true, effect exists, null hypothesis is false. I fail to reject. My type 1 error is when I reject the null hypothesis when the null hypothesis is actually true. This is my type 1 error. An effect exists, I've just failed to detect it, I fail to reject. This is going to be my type 2 error. Okay? And so typically what we are worried about in terms of sort of managing this error matrix here, we often worry about our underpowered studies, right? This is where our power analyses come in. This is where we want to know how many people do I need to have in my data to reasonably detect this effect that I'm expecting in the population, right? But we can also have overpowered studies too. Saying here overpowered studies can result in misguided inference. Anybody give me an example where overpowered studies might start to become problematic? Awesome.
You just have like a bunch of people and they're happen to sample the wrong.
What's that?
Session. Like if you have a bunch, like if I took one school, like I take UI out and then apply it to all schools, you'd have a huge sample size, but there's just a lot of white people here, so
okay.
It might not be applicable.
Okay, so I've got a big sample, I've got a lot of data, so I've got kind of an overpowered study, but then sort of questions about generalization to sort of other stuff, that could be sort of something going on. Anything else come to mind in terms of overpowered studies, what that might lead us astray? Talk about this in terms of a fundamental problem with null hypothesis testing. If I get enough people, what if I stakes this significant effects? If I have enough people, any random variables that I look at, because the correlation or the difference is never going to be exactly zero. It's always going to be something, right? And if I have samples, so I'm doing a project working with some Census Bureau data and things like that, and I don't want to go through. I'm like, oh, can we go through and take this, that, and the other thing? And like, well, you're probably not going to have a sample big enough to look at that. You're probably only going to, by the time you go through and cut this all down, you're probably going to have, only like maybe 200,000 or 300,000 people in there. Like, that's so big. Like, if I'm an economist, right, and so I'm used to working with data sets that have millions and tens of millions, hundreds of millions of observations, then maybe 20,000 people is a sample that I can't do anything with. But for me, never seen a sample that big in my lifetime, right? But the problem is if I get samples that big, right, it doesn't matter sort of what question I ask, it's all going to come up as statistically significant, right? And the only thing that statistically significant means is that this point estimate is not exactly zero, right? And so what we can do is start to over-interpret things with overpowered studies where we're saying, oh, we've got a significant effect, when in actual fact the magnitude of that is sort of not practically important for theoretical or practical reasons. This is one to sort of keep an eye out for that. All right, questions on any of this? Okay, so covers traditional null hypothesis, right? This is what we do. This is sort of what our whole science is based on, is this procedure of null hypothesis significance testing, okay? The question is this a reasonable procedure? Is this, can we pull reasonable inferences from this thing that we all have agreed on, that this is how we're going to structure our entire science? Is this a reasonable thing to do? And people consistently, for decades, have said there are real problems with the way this is with the way this is conducted. And people have gotten, people who are important and sort of can get more. If you're a big name, you can start to get more creative in how you're sort of describing and conceptually. So if I'm Paul Meal, I can sort of make up whatever sort of analogies I want to, right? Null hypothesis testing describes a potent but sterile intellectual rake who leads in his merry path along a train of ravished maidens, but no viable offspring. So it's my null hypothesis testing right here, right? But equally creative, right? So we got Cohen talking about naked emperor shamelessly running around, right? So we've gone through and we've said Hobart in 2019, so there's a recent special issue by American Statistical Society or American Statistical Association, talking about sort of this whole process of categorizing things as significant or non-significant is not justified. It's never been justified. We do it, but it's problematic for so many reasons. With the ASA statement here, including it's time to stop using the term statistically significant entirely, nor should variance such as statistically different, p less than 0.05, non-significant, whether expressed in words, asterisks, or this is pretty extreme, right? This is currently best practice recommendations by statisticians, right? And so this is hard to work out from sort of our standpoint, because we're not statisticians. We use these tools. We're not the people who develop them and sort of study them, right? And our entire system of publication and getting things put together is based on this idea of statistically significant results, right? But if we've got people who study this and do this, and this is their sort of specialty, saying that finally, and this has been something that worked in the works for a long time, finally to the point where they're saying, as a society, as a group of professionals, we're saying that we shouldn't be saying statistically significant. Sort of this dichotomization of statistically and not statistically significant is no longer reasonable. As users of this, we should probably start thinking about, okay, is it time for us to start trying to shift it and go through and change it and sort of do different things? Sort of feel about like if I study, if I'm a clinical psychologist and sort of my entire life is studying the effects of psychological treatments and empirically support evidence-based therapies, hopefully people who use these are listening to sort of my recommendations for best practice on how to implement things along those lines. We talk a lot about in our field about best practice and evidence-based stuff. We can't just pick and choose when we want to do evidence-based stuff. And so, again, one of the things that I've done with this semester, I'm not going to tell you, and I'm not going to sort of say that you shouldn't use the term statistical significance. It's super controversial, and sort of this is kind of the foundation for which our sciences sort of threshold for publication is built on. If I'm on a committee and you identify something as statistically significant, I'm not going to slap your hand or try and fail you or things along those lines. But what we're going to try and do over the course of the semester is give you language that's better for qualifying what we're seeing in our data and how to describe it in ways that don't necessarily have to fall back on dichotomization of statistically significant and non-significant. Okay. Quick. So is that greater than or less than 0.05? Okay. Yeah. Chris, is that less than or greater than 0.05?
That's less than.
Nick? Greater than. Okay, cool. So everybody can identify things that are greater than or less than 0.05, all right? If our rule is that anything that is less than 0.05 is statistically significant, if it's greater than 0.05, it's not statistically significant. Is that statistically significant, Alicia?
Yes.
If it's less than 0.05, it is. If it's over 0.05, it's not. Not statistically significant. No problem. Chris, statistically significant, not statistically significant?
Statistically significant.
Okay, cool. You guys have got this. We don't have to spend a whole 2 semesters talking about whether something is or isn't statistically significant. So, as we move forward, if you choose to, in your own research and sort of in your lab and things like that, sort of identify things that's statistically significant, not statistically significant, do that. Cool. I'm not telling you can't say statistically significant. I'm not here to tell you that you have to rail against the universe and revolutionize things from the inside. But what I'm also going to do is you're going to challenge, all right? You're going to try and spend this whole semester, if you can work through your problem sets and not rely on identifying things as statistically significant or not significant. I told you I was going to give you bonus points if you found a picture of staying up, police out. I lied, that wasn't, but nice work with that. With this, so I will give people, like, if we go through, I'm going to like start having you sort of count the number of times you identify as something statistically significant, just to see if we can do it, right? For the purposes of this class, as we're describing things, can we go through and, I'm not going to take points away from you if you do, like I'm not going to sort of do that. And in your own labs, if you're going through and sort of this is convention and this is, you're young people, you're trying to publish and just sort of get things out. I'm not here to say you need to fall on your sword for other types of things, but what I'm hoping to do this semester with some changes is trying to give us a language to use things that are consistent with best practices so that we don't always just have to say, this is significant, not significant, as we're moving forward. So, does that sound like a fun challenge? It does. Okay, what? Sorry, yes, I'm like, what? So,
Right, more questions,
Right.
all questions. So if they're trying to get away from this dichotomy of significant and not significant, how does that play in with a dichotomy of null, not null?
Yeah.
Like,
and we hold on to that because we're going to go through and start talking about problems with this and sort of functionally what's happened because of our reliance on sort of just identifying this bright line threshold of if that p-value is anything less than 0.05 or less, we call it statistically significant. If it's above, we say it's not significant. And some of the problems, both conceptual and methodological issues with this as a system for decision making, and most importantly, inference. Okay? So, if we're thinking about both conceptual and methodological problems with sort of our traditional approach to null hypothesis significance testing, at a very basic level, Cohen talks about difference with sort of the fundamental logic and sort of the structure of how the logic of null hypothesis testing is put together. Anybody here philosophy majors or studying philosophy? Okay. Well, if we're thinking about just from a basic logic approach, right, we start to get into problems with how we're structuring these questions. So the scientific question that we have, given these data, what's the probability that the null hypothesis is true, right? So given the data that we collected, given what I've observed, how likely is it, or what's the probability that sort of this null hypothesis is accurate? That's what we want to ask, right? That's the question, that's the scientific question that we have. The question that null hypothesis testing is providing us is that given the null hypothesis is true, we're assuming the null hypothesis is true, what are the probability of the data, right? So the question of interest is, given the data, what's the likelihood of the null hypothesis? What we're actually getting is, given the null hypothesis, what's the likelihood of the data? It sort of flips this around, right? And so if we're working in absolutes, and from a logic-based standpoint, if we're working in absolutes, if we say, if the null hypothesis is true, these data cannot occur, right? if the null hypothesis is true, these data are impossible. We say these data have occurred, therefore the null hypothesis is false. Is this reasonable? Yep, this works. Logically, this is consistent, right? But what we do with our null with our significance test is we change this a little bit. We take it out of the realm of sort of concrete and certain and start to talk about likelihoods and probabilities, right? So this is fine, but this isn't what we do. What we do is we say if the null hypothesis is true, then these data are unlikely to occur, right? This is what happens when I get that p-value of 0.005. Say if the null hypothesis is true, we would expect a sample this extreme or more 0.5% of the time, right? So we're saying if the null hypothesis is true, these data are unlikely to occur. These data have occurred, therefore the null hypothesis is unlikely to be true. This is sort of the logic of our null hypothesis testing, right? I mean, three people sort of seeing what we've got going on here. But these two things are different. And if we start substituting different things, we can see how this doesn't make sense, right? So if I use this logic, and I say if a person is American, he or she is unlikely to be a member of Congress. That's true, right? This person is a member of Congress, therefore he or she is unlikely to be an American, right? It doesn't take too much to start to show the fundamental flaws in the basic logic of our null hypothesis testing. What we want to do is we want to say, if the null hypothesis is true, then these data probably can occur. But this happens all the time. We see things all the time that sort of follow this, right? And so we've got problems with the fundamental logic. Cohen referring to this as the illusion of attaining improbability, right? But from a basic logic structure, it doesn't map out. We also have an issue of non-equivalent probabilities. Again, going back to what we just talked about, we say our scientific question here: what's the probability of the null, or what's the probability that the null hypothesis is true given the data? How likely is the null hypothesis, right? But again, what we're getting with null hypothesis testing is what's the probability of these data given that the null hypothesis is true. And if we go through and put this in probability notation, we can shorthand this. We can say the probability of the null given the data, that's what we're asking. But what we're actually getting is the probability of the data given the null. And these two things seem like they should be sort of pretty close to one another, kind of interchangeable, when in actual fact they're not. They're quite different in many circumstances. Okay? So again, and this is sort of what we do in logic, like I'm sort of part of the community. So, but if you're working with sort of logical arguments and things like that, sort of going through and giving examples, right? So if we say the probability that you speak English if you attend this class versus the probability you attend this class if you speak English. This 100%. This not 100%. And there's 300-some million people in the United States. 70 of you are in this class, right? This is a very high probability. Almost probably this is probability 1. This is something that's infinitely small, right? We're just taking these two propositions and switching them around, getting entirely different probabilities. Okay, and so what we're wanting to do with the null hypothesis testing, what we're trying to set up is we want to reject the null hypothesis to conclude that the null hypothesis is unlikely, right? What we want to do when we reject the null hypothesis is we're saying these data, assuming the null hypotheses were true, these data would be very unlikely, and so then as a consequence, the null hypothesis itself is unlikely. But what ends up happening when we get into the calculation of this, it starts to get really complex. In order to make this statement, I need to have some information that we often don't have or rarely have in terms of our statistical testing, right? What we need to do in order to properly calculate the probability that the null hypothesis is false is we need to have some prior probability. I need to know beforehand, before I collect the data, what the likelihood of the null hypothesis is being true relative to the alternative hypotheses. Anybody here ever been exposed to Bayesian methods or Bayesian statistics or heard of anything like that? Yeah. So this is a whole sort of approach to Bayesian statistics, is sort of saying, okay, our null hypothesis procedure is flawed because it's not asking the questions we want to ask, or it's not answering the questions we want answered. But in order to answer the questions we want answered, which is some of these Bayesian probabilities, we need to have more information about the probability of this thing happening before we collect data. We often don't have that, which means we have to come up with something, and then depending on what that probability is, it starts screwing things around. I can start, the concerns, I start sort of putting my thumb on the scale, right? But what we can do is we can go through and do a demonstration and we think about some things that we do know prior probabilities for. So let's say in this example, and so I pulled this from Cohen, base rate of schizophrenia in the population is 2%. Actually, no, it's 2%, that seems high. Schizophrenia should be probably lower, but let's say that it is, right? So we know based on epidemiological research that the probability of schizophrenia in the larger population is 2%. So the probability of a schizophrenia case is equal to 0.02. And what we have is a screening measure that has 95% accuracy for diagnoses, 97% accuracy for negative diagnosis. Okay? So if we're going through putting this into sort of terms, right? If we see HO, the case is normal. So null is the people, the person who's come in doesn't have schizophrenia. Our alternative H1 is the case has a diagnosis. So this is the truth. This is what's actually true in the universe. T is going to be our positive or negative test. And so if we look at the probability of a positive test given an actual case, it's 0.95, right? This is my accuracy. So if a person comes in and they do have schizophrenia, the 95% chance that this test is going to come up with positive, we're going to detect it. On the other hand, the probability of a negative test given a non-case, 97%, even a little bit better, right? So if someone comes in and they don't have schizophrenia, the likelihood that they get a negative case is 0.97 or 97%. Who's excited about this test? I'm excited about this test. I don't know if you ever looked at sensitivity and specificity rates of our common clinical measures. They're nowhere near this, right? This is an excellent, excellent, excellent test, right? So if we go through and we want to see, if I want to calculate the probability of a positive test given a case that does not have schizophrenia, that's going to be 0.05, okay? Probability of a positive test given a normal case, I take 1 minus sort of this right here, gives me 0.5. And so from a null hypothesis test, what we would say is we would conclude that this outcome is unlikely, and we would classify the case as consistent with diagnosis, right? So I know that if I have a positive test, so if someone someone comes in, they have schizophrenia, likelihood of positive test is 0.95. If someone comes in, they don't have schizophrenia, they have a negative, the probability of a negative test is 0.97. So the probability of someone coming in and having a positive test who actually doesn't have schizophrenia, I'm going to say that's really low. And probably what I'm going to do is I'm going to believe the test and classify this person as having schizophrenia, right? Based on my stuff. What I've done here is sort of committed this logic fallacy that's at the center of our null hypothesis test. And what I've wanted to know is the probability of the data assuming the null, right? That's not the probability of the null assuming the data. It switches things around. Okay? So in this case, what's the probability of a positive test given probability of the data assuming the null is true is very unlikely, right? The probability of a positive test giving no case, we calculate that as very unlikely. This is a different thing than the probability of no case given a positive diagnosis. What we need to do to calculate this is start to use some of those Bayesian statistics. And this is the formula that we actually need to calculate this probability. We won't go into all sort of what this is going on, but if we go through and we take the probability of the null hypothesis, the probability, frequency of diagnosis is 2% of the population, the probability of normal cases is 0.98, times the probability of positive test given a null result, times the positive probability of a null result, times the probability of a positive test given null, probability of a positive case, times the probability of a positive case given, or positive test given a positive case. We go through and calculate this out. We find that the probability of a normal case given a positive test is actually incredibly, incredibly high. Okay? So this thing that we identified is unlikely, right? Using our sort of normal structure and logic for null hypothesis testing, we've deemed this as unlikely. We've said that the probability of a positive test, assuming a normal case, is extremely, extremely rare. And so if someone comes in and they have a positive case, I'm just going to say, nope, this is a case, because this is something that doesn't happen. But if we actually calculate this appropriately, we find that the probability of a normal case given a positive test is really big, right? And so we wanted to plug some basic numbers in here to kind of look at this. What we've got here is we've got our sample of individuals who don't have a diagnosis and people who do have a diagnosis, right? And we have the number of negative tests and the number of positive tests, okay? And if I'm going through and I'm looking at these sensitivity and specificity figures, what I've done, if I'm looking at my, specificity here, the probability of a negative test given a non-case, I'm going to take this right here. So someone sort of pull out. Who's got a calculator? Okay, tomorrow's got one. Right? If I take the probability of a negative case given a normal, the probability of a negative test given a normal case, 949 divided by 979, where do I get? 0.969, right? So that's what I've calculated. If I take the probability of a positive test given a positive case, if I go through and I take 20 divided by 21, what do I get? 0.952, right? So these are the statistics that we're calculating to get this, right? But this isn't what I'm actually asking in this question. What I want to know, what's the probability of a positive test given a normal case, right? So of the 30 cases that tested positive in normal folks versus the total number of positive tests, 30 divided by 50, 0.6, right? So this is where we're at with this stuff, okay? Anybody having a hard time wrapping their head around this? Yeah, okay. It starts to become hard. So we've got sort of inverse probabilities here. Go through, take a look at this slide and sort of work through some of the notation, right? But sort of at the end of the day, what this is a demonstration of is what are the inferences that we're making from our null hypothesis procedure and things that we identify as, oh, this is probably quite unlikely, and so we're going to say that this is actually, we're going to reject the null hypothesis because this event is actually unlikely, is not actually addressing the scientific question that we want to know. What we want to know is, based on the data, how likely is the null hypothesis? What we're actually getting is what's the likelihood of the data assuming that the null is true. And if we start sort of playing around and we're not careful about this, we can start to come up with conclusions that map not on sort of reality of the situation. Now, anybody know why we're getting such a discrepancy between this and this? This is a base rate issue, okay? If the probability of base rates of schizophrenia in the larger population was about 50%, you'd probably see less of this going on. But particularly for things that are very, very low base rate, things that have very, very low prior probabilities, we can start to get into some problems in terms of how we're going through and thinking about things. Okay. Questions on this? Okay. So, demonstration of sort of what's going on from a practical standpoint with the non-equivalent probabilities. So again, sort of what all this is going through is sort of the potential errors we can start to make if we use p-values to infer truth of the null hypotheses based on the sample data. It just doesn't map onto what we're actually wanting to get. Okay. All right, other criticisms. Null hypothesis is always quasi-false. And we've talked about this a little bit, right? The whole system is bent on trying to determine whether or not the null hypothesis is false. That's what we're testing. But there's a strong argument made, and from a conceptual basis, null hypothesis is always false, right? If I go through and I carry out sort of the decimal place far enough, eventually it's never going to be identical. It's always going to be the exact same thing, right? And so we see 2B, is it foolish to ask, are the effects of A and B different? They're always different in some decimal place, I like this Thompson quote here, talking about, we make a big deal about rejecting the null hypotheses, when functionally rejecting the null hypothesis is about getting a large enough sample size to determine that, yep, it's not exactly equivalent, or the groups are not exactly zero, right? So then we conduct this statistical test to evaluate whether there are a lot of subjects, which is essentially what we're doing. Do we have, p-value is telling you essentially, like, do you have enough people, right? And if I got enough people and I reject the p-value or reject the null hypothesis, I know this is going to happen because I've spent a lot of time getting this massive sample, right? And so what Cohen will talk about is if the null hypothesis is always false. If we know that the null hypothesis is never, ever true, it can't be true. What we would expect then is that we're going to reject the null hypotheses in the direction that we want at least half the time, right? If the null hypothesis can't be true, if you're either on this side or this side, right, then at least half the time, irrespective of what I think, right? I've got a theory that says eating pathology is driven by evil entities sort of going through your spirit, and so we're going to see this as elevated blood pressure relative to something else, right? That's my theory, right? And then I find that people with eating pathology have elevated blood pressure. Yes, evil entities score, right? I can come up with whatever harebrained hypothesis I want. If the null hypothesis is always false, I'm going to be right half the time. This is flip a coin, right? From a conceptual standpoint, to the extent that my weird hypotheses start to align with more plausible hypotheses, the likelihood of me claiming support for my harebrained hypotheses is going to start to increase, right? And so, at best, that's the worst possible scenario. We're going to support incorrect or irrelevant theories are going to be supported at least half the time as our power increases. As our power starts to get larger and larger and larger, we're always going to reject the null hypotheses. The question is just which direction does it go? Does it go trivial direction in this way, trivial direction in this way? But based on the rules of our test, I can claim statistical significance and claim support for my theory when I shouldn't be doing that at all, right? And so Neil calls this a correct factor. Everything's related to everything else. If I get a sample of 1 million people, I can take any variable, correlate it with any other variable, and it's going to be statistically significant. That doesn't necessarily mean there's a meaningful link between those two things. It just means that the correlation is not, the estimation of my correlation is not going to be exactly zero. People see sort of the logic behind this criticism that the null is never, the null is always false. The null can't be true. Physically impossible for the null to be true. And so then the question becomes, if it's never true, then why are we so worked up about it? Like, why are we so interested in saying that the null hypothesis is false, right? And so what our statistical test is saying that some value is not exactly zero, right? It starts to become hard to start to envision and thinking about examples where the fact that something isn't exactly zero is relevant or meaningful, okay? Again, with our null hypothesis, if you see something that's statistically significant, if you guess and put money down, that means that some estimate, some value is not exactly equal to zero, you're going to win like 95% of the time. You'll be a rich person. So see if you can make that bet in Vegas, right? If you start to think about what does it mean if something's not exactly zero, a lot of this doesn't start to have any real practical impact. Let's say I've got an experimental manipulation that results in 1/20th of the standard deviation increase and a decrease in my outcome. It's not zero, but it's minute, right? I've got 500 people in my sample. I just say that it moves it a little bit, right? Whether or not that's that 1/20th of the standard deviation increase or decrease in outcome probably isn't terribly meaningful in terms of sort of testing whatever I wanted to do. I can say it's a statistically significant effect, but it's just not practically meaningful, right? Same thing, I've got intervention produces a change in self-reported symptoms that's not zero. If I'm a client, am I pumped about this? Probably not. Like, I don't care if the change in my symptoms is just not zero. I need to have a change in my symptom that's something that's reasonable, that's sort of impactful in terms of me. The fact that it's not zero doesn't really matter, right? I spend multi-million dollars to improve air quality or reduces pollutants by 0.5 parts per million. I don't know. I kind of made this up. It seems like a small number. It might be a huge number. I don't know. I've got a friend who does this stuff. But again, thinking about sort of the time and effort, the resources to implement this stuff doesn't make a difference. I can say that it's statistically significant. Whether or not that actually confers anything meaningful is a completely different situation, okay? And so the problem is that people who talk about, criticize our approach to hypothesis testing is it doesn't account for and it doesn't capture the magnitude of effect. All it does is it captures how many people we have in the sample, but if we go through and we say that we have a statistically significant effect, it implies that it's meaningful, right? When in fact, many times it might not have any practical implications at all. Again, the argument for, again, eliminating statistical significance from our lexicon, statistical use of the word significance, never understood by those without statistical training to mean anything less than its synonyms, important and influential. And this is a pretty generous quote because by those without statistical training, even people with statistical training, they go, this is a significant effect. I go, well, that's cool, that must be important. When in fact, if we're actually looking closely at the research, it just means that it's not, at least based on the data that we've collected, it suggests that it's not, the difference isn't zero, or the effect isn't zero, which might not be terribly useful. Other criticisms against dichotomous decisions, right? So this sort of P of sort of basing statistical significance as an index of replicability. We have, and it's hit experimental more directly, and the experimental have been working at it for a longer time than us clinical, but we're going to get there eventually. So this problem with being shocked when things don't replicate, right? But if we're basing our expectations of replication on whether or not something is a statistically significant effect or not, this is a terrible, terrible gauge of the likelihood of replication. So this is an example from a Cumming textbook. We say we've got a pair of studies evaluating the efficacy of new intervention for insomnia. Based on a sample of 44 individuals, Luck 2012 noted a statistically significant advantage of the intervention relative to weightless control. By contrast, no Luck failed to observe a statistically significant effect in a similar sample of 0.6, 2.2 in the non-significant standard deviation of the difference, a little bit lower here than here, but we've got a big difference in the p-value, right? Luck, very clear statistical significance of this effect. No Luck, so everything's a wash, right? And so what we would say here, so what would, Chris, what would be the standard conclusion across these two studies?
The standard conclusion would be that Lucky's findings is statistically significant and No Luck's findings are not statistically
Right.
significant.
And so what would we conclude about the state of this research?
That the intervention couldn't be replicated.
Yeah, it couldn't be replicated. The data is mixed. It's inconclusive, right? We don't have good evidence for whether or not this. We have one study that found a significant effect, other study didn't find a significant effect, right? But if we're looking at things closely, sort of asking about, do these studies provide consistent or inconsistent information, right? And sort of what types of things can we conclude based on sort of this limited research, right? We're often faced with this decision, right? I'm interested in this very specific effect that people haven't really looked at. There's a couple of different studies. This one's found it's significant, this one doesn't found it's significant, so what do I conclude from this, right? If we're using statistical significance as our indicator, we're gonna miss a whole lot of stuff, right? If I go through and I calculate the confidence interval around the difference in both of these studies, the 2012 study had a difference about 3.5 points, No Luck 2013, about 2.2. But if I look at these confidence intervals, Nick, what am I seeing in terms of these interval estimates here?
They're really not all that different.
Yeah, there's a ton of overlap, right? If I go through and I plot out these confidence intervals, if you're looking at meta-analyses, right, those are those, what is the meta-analysis plot where it's got sort of different effects and intervals? There's a name for it. But basically across individual studies, right, looking at sort of point estimate of the effect, the confidence intervals around those effects. If you look at the confidence intervals here, I would say that these two studies are actually telling me kind of the same thing, right? They're not terribly inconsistent. We've got one study that had a few more people that ended up being statistically significant. The other one wasn't. But in terms of the data that they collected and what it actually looks like, it's pretty similar, pretty on point, right? If we go through and take a look at calculated effect sizes, we'll get into in the next lecture. Here we got an effect size of d equal 0.52, so we've got about a half standard deviation difference between treatment and waitlist controls. Here, we've got a standard, an effect size of about 0.3, so about 0.3 of a standard deviation between controls and treatment. But they're both going in the right direction. Now, I don't know if a half a standard deviation between treatment and not treatment, or a third of a standard deviation across treatment and not treatment is meaningful. But it's at least saying that things are going in the right direction, right? But if I'm not looking at this, if I'm just using statistical significance as my determination of whether or not we're on the same page with stuff, I'm going to come up with a very different and probably misleading conclusion and start to get all worked up about replication versus if I'm actually looking at the effects that have been calculated here. Questions here? All right. We also see that we've got bias against the null. When we're going through, and for a good reason, it's the way the whole system is set up, what we do is we tend to associate our predictions with the rejection of the null, right? And then if we don't reject the null, right, if we don't find claims of statistical significance, what happens to our study? I think we should.
We don't find
Yeah.
significance.
Do we get to publish that study? No, we don't, right? And so it goes in sort of like failed experiments, right? And then we do another one, right? Tomorrow you do another study, and you fail to find statistical significance. Do you get to publish that study? No. And then we keep doing this and doing this and doing this and doing this, and a bunch of people all over the world just trying to sort of do the same thing, and we keep finding that sort of we're failing to reject. There's just not a meaningful difference in this stuff, right? But then Nick runs a study, and Nick has the best intention. He did everything right, but he just happens to get a weird sample where all of a sudden he did find that effect was statistically significant. Does Nick get to publish his study? Nick does get to publish his study, right? And Nick gets a big splash because he's found this thing that is really intriguing and everybody's super excited about it, right? But if we think about the null or the distribution of possible effects, right? And this is sort of the mean effect, right? In the population. Like this is the population effect, right? And everybody's kind of finding stuff kind of around here because this is the population effect. But then Nick happens to, through no fault of his own, get something out here. He gets an effect of 2, right? Now, Nick doesn't know everybody in the universe, and he doesn't have a spreadsheet of everybody who's tried to demonstrate this thing before. So does Nick know that his test is way out of bounds for everything else? You don't know. You're just super excited, right? You've made yourself a line in a research career and things along these lines, right? And so what ends up happening for anybody else, whoever goes through and tries to replicate Nick's effect or tries to do this, what are they going to think is the population effect that they're looking for? That, right? When in fact, this is the population effect. But all the stuff that was close to around sort of what the true population effect is, that got filed drawered. It never got published. No one knows about that stuff because it never saw the light of day. And this is the problem with this dichotomous decisions, is we have a bias. We don't publish null effects. Even when null effects are probably kind of meaningful. If you've got it, so this is where this idea of pre-registration comes in. If I've got a good idea and I've got a good method, I'm saying, hey, this is what I'm going to do. And so you're submitting it to an article or a journal and saying, this is what I want to do. So whether or not I find actually, regardless of what it turns out, even if the whole thing comes up a wash, that's still important information, right? These are the types of things that are starting to come on as sort of a possibility, right? So recognizing that null effects can be important, and they start to inform the literature, because what ends up happening is if I'm looking at just the effects in the available literature that we're all working from, almost certainly massive levels of positive bias based on what's being published, because we just have this this bias against publishing null effects. And so what ends up happening is now that we've got 1 or 2 studies that all have fallen way out here, right? 2 things happen. Everybody else who then tries to publish, they're basing their power analyses on what Nick found, right? And so based on what Nick found, I should have 30 people in my sample and find this easy, right? Problem is, this is a bias effect. This isn't a reasonable effect. What the effect is actually down here, but we don't know about that. So now we're all bent out of shape because we can't publish or replicate Nick's findings, and we're mad at Nick, like Nick did something, right? But if we understand sort of basically what's going on, we shouldn't be shocked that we can't replicate this stuff, right? The whole system is set up to massively overestimate everything that we think we know about things, right? And so this starts to become important for meta-analyses. Good meta-analyses involves not just going through the published literature, but unpublished stuff. We're going through dissertations. We're reaching out and saying, do people have data on this stuff? Starting to go through, see if we can start to get other data sets that tried to capture this effect, but then sort of weren't successful and so didn't get published, and then calculating some statistics based on whatever we are able to estimate. So then looking at, talk about this, a file-to-drawer effect. How many studies would have to come up with no results before this to cancel out this effect, right? And if it's, there would have to be 100 non-published studies in order to cancel out this effect. Well, it's probably not 100 non-published studies, right? But if there's, 10 non-published studies that we don't know about would cancel this out, then I start to become very concerned about sort of the stability of that effect, right? And so we start to see also, we already have problems with sort of just the way our literature is set up, and where there's sort of hyper-focus on this potential for type 1 error. I basically forced Nick to do this, right? Like it's not Nick's fault, but what we do is we go through, and if we go through and we start sort of alpha correction for multiple comparisons and things like that, which are important. But every time I do that, I just crank up the knob in terms of how far that effect has to be in order for it to be published. And so if I do that, what I'm doing is likely to increase the threshold for overestimation of effect size. I'm pushing anything that gets published. If I say, all right, now instead of right here in order to be published, you have to exceed this in order to be published, I've just made this whole situation worse, right? So my effort to really say, boy, I don't want anything in the literature that's not replicable. I want to have very, very strong evidence that this is a real true effect before I'm going to publish it, right? And so in terms of recommendations for how to change our field, there's been some suggestion that instead of alpha 0.05, in order to claim statistical significance, we set it to 0.005, right? And the idea is that if you hit 0.005 in terms of your p-value, that's going to be, should be easier to replicate things like that. But so the idea is good, or sort of or understandable, but probably what's going to happen is that's just going to make this whole situation that we already have even worse. Because now the stuff that's going to get published is stuff that's super greatly extreme. So again, some more Cohen stuff. We're talking about the potential, sort of unqualified or sort of not thinking carefully about what happens if we start cranking up our alpha levels or von Ferroni correcting for everything under the sun. You'll see this. You'll get a paper out and someone will say, oh, you have to von Ferroni correct for the 20 different comparisons that you did. That's stupid. Like, that's not what that test is for. And one, maybe you shouldn't have 20 comparisons in there, but also correcting for all 20 of those doesn't make any sense. Okay. Other stuff, we've got bias in terms of how we interpret things. Okay. When we dichotomize our results into statistically significant, non-significant categories, this would be fine if we gave both of these decisions equal weight. Okay. If we said statistically significant, not statistically significant, if we got to use the same criteria or the same inference or the same sort of level of inference, we probably wouldn't have a huge issue. But what ends up happening is for effects that fail to hit our traditional standards, we interpret these as inconclusive. Okay? If we're doing a good job. I found a null effect, and I say, well, based on these data, I don't know, they're inconclusive. I'm not saying that there's no effect, I'm just saying that I don't have enough evidence to claim an effect. That's sort of the best case of how I should be interpreting those null results. But what often happens, far more often, is people interpret null effects as no difference, as no effect, right? So if I don't find anything, I'm saying, oh, it's inconclusive. But if I do find an effect, if I do get an effect that meets criteria for statistical significance, what I do is I accept this as conclusive. What I do is if it tips over, it's 0.049, if it's 0.052, I say, I can't say one way or the other whether or not this is an effect or not, right? But if I go to 0.049, what I do is I say, this is a significant effect, this is a thing, and treat it as if it is sort of absolutely, sort of 100%, this is a thing, right? And because of this bias in terms of sort of, we're not using equal criteria, what ends up happening, we end up far over with the dichotomous decision making, end up far overestimating and pulling in far too much inference about sort of what our effects mean. We place more confidence in this than is warranted, given what we know about our statistical tests. Okay? So essentially, what we have: heads I win, tails you lose, right? And so this is the argument is that embedded within this whole system, I have a false sense of security for both the existence and replication of significant effects, right? And then we're bummed when things don't come out. I've seen this before in meetings where like, well, Siley found sort of this effect or this relation or this difference with a sample of, she found a significant effect with a sample of 20, and so therefore I'm just going to collect 20 people and I'm going to find the same thing that she did. It's a fundamental misunderstanding of the whole situation, right? Because one, Saley's effect is probably sort of massively exploded and way too big, right? Two, when I go through, I'm going to be doing a different study with a different population, things along those lines, right? I need to go through, just because you found something that's statistically significant doesn't mean that I'm going to. We'll later read a paper by Greenland looking at the relation between p-values and replicability, in terms of replicability being sort of reject, not reject, and basically arguments in that paper saying that effects that are found, if you did a perfect replication, an exact replication of a study that found an effect at p equal 0.05, your likelihood of rejecting in the same direction is about a coin flip. It's about 50%. So if you're looking through the literature and you find, Chris, you find a study that's done something, looks pretty cool, but their p-value on that effect is about, right around 0.05. If you were to do an exact replication of that study, pull from all the same sample, pull from the exact same population, using the same sample size, and getting the same effect size in there, your likelihood of also rejecting the null hypotheses, again, is about a coin flip, right? But what happens is we put far too much emphasis on this effect because it's statistically significant, it creeps over a line, and then we expect to replicate when in fact that's probably not going to happen, or it might. It's an even bet, it's a coin flip, right? It means there are worse bets you can make, but then we get really shocked and upset when we have stuff going that doesn't work out the way we'd hoped. So, and this is what we do, right? We get something 0.05, we get super excited about it, like, yes, it was a groundbreaking stuff. Probably this is what we should be doing, right? So to be much more skeptical, think about like, is this something that's reasonable to go through and think about? Okay. Question? So as I was talking with Tara, and so what I was going to do, I'm going to have a main, so this is, we get too, the sort of argument is that we get too excited about stuff that's 0.05, which probably shouldn't be because it's pretty inconclusive. We get super jazzed about the whole thing. I was going to have a meme that said, don't be thirsty. But then I asked Tara, I was like, can I say that? She's like, no, I think that means something different. I'm like, I think it just means that you're just overeager. She's like, no, I think it means throw a Title IX complaint on you or something. I don't know. Can I say that?
Yeah. It's like scientific thirst.
Scientific thirst, right?
Yeah, what are your search terms on the internet? Like,
what's up?
Where, how are you pulling these pictures?
This, I was trying to like, am I like super excited guy? And then skeptical person. Yeah. I don't know. My search history will get me fired eventually. Stuff comes up that I'm not looking for. All right. Last criticism, I think. Maybe it's not. Failed to recognize the limitations of our procedure. Again, our test provides us, our p-value uses an index of the probability of obtaining results as extreme or more extreme than those observed in the data, right? Assuming that no and all auxiliary hypotheses are true. But what we fail to recognize and sort of don't take into consideration is all of these auxiliary hypotheses. Again, we have representative samples, randomly selected samples. We don't have any violations of our underlying data. Our hypotheses were generated prior to the evaluation of our data. Why is this important? yeah, my likelihood of finding something after I find the data, or after I look at the data, starts to go through the roof. Like, oh yeah, of course that makes sense. Why did I thought about that beforehand, right? Well, basically what you're doing is you're cherry picking sample specific stuff, and then deciding that you were interested in that after you saw that it was statistically significant. This is incredibly problematic, right? We talked about model specification. We've included all our variables that are measured through valid. Our statistical models assume that we're measuring things without error. Do we ever measure things without error? Nope, we don't, right? And so all of this stuff sort of goes into sort of the background, and we forget this. We don't go through and we don't think about this. And so things that our null hypothesis tests do not provide, probability that null is true or false, right? Our p-values tell us the extent to which our data are consistent with the data, assuming the null hypothesis in the underlying model, but it doesn't tell us whether or not it's true or false. It doesn't tell us the probability that data were obtained by chance alone, right? Mathematically, it does, because the whole structure is assuming that we're in a perfect vacuum where we've achieved random samples and sort of everything is conducted without error. But in actual fact, our samples aren't random. Our methods are often not great. There's all sorts of systematic biases that go in there, and so we can't conclude that our p-value is telling us the probability that our data were collected by chance, because there's a lot of other stuff that starts to go through and drive that data. Estimate of the magnitude of effect, probability of replicating parameters. Again, this is where we start to go through, and again, this is part of the argument about getting rid of the phrase null hypothesis or significant statistical significance. People who work in this area, people like me, consistently misinterpret this type of stuff. And a lot of it's just because of our training, and a lot of it's because sort of the technical aspects of things get kind of tricky, right? And so the argument is, there's arguments being made that, well, it's not a problem with a hypothesis test. Hypothesis tests are just doing what they're supposed to do. It's us dum-dums who attach unwarranted conclusions about it. Well, that's true. And people should interpret things correctly, but they don't if I'm working in a world where I'm just worried about that most of the time, right? But we know that even people who are trained go through and commonly misinterpret p-values. We also know that our p-values in our tests don't provide support for a proposed theory. Again, thinking about Chris, front row Chris, I can see you're already excited about my evil entities theory about sort of eating pathology and sort of things along those lines, right? If my evil entities theory of eating pathology starts to align with more plausible cognitive behavioral hypotheses, I'm going to find a lot of evidence for my evil entities therapy, right? Our tests don't give us direct evidence for the theory. We have to put that together through critical assessment, reasoning, and things like that. So again, this is going back into the 30s. Fisher's identified saying no isolated experiment, however significant in itself and sufficient, can suffice for experimental demonstration of a natural phenomenon. A single study tells us very little about anything, right? At best, we've got a really compelling study that suggests a direction for future investigation, but we can't reasonably interpret any individual study without the context of what's already known. So again, this is all kind of what we think we're doing. We're in the control panel, so we're the statistical test because we got fancy, we got the new version SPSS, right? In actual fact, is it kind of just bundling along, trying to figure things out, sort of tripping over stuff that we think are things, but they're not things, right? Again, sort of going back on this idea of sort of understanding the limitations of our procedures, right? We've got what we've got, and we're getting recommendations for things to fix it, but I don't know that any journals that any of us are going to try and publish in anytime soon are going to say, oh, we're just going to do it away with statistical significance and null hypothesis testing. So the best we can do is just start to recognize the type of things that we're doing, sort of the limitations. So there are a few issues with our sort of entire approach to knowledge, right? Going down through sort of summarizing the stuff that it's a lot of things, right? And I don't know, it just, not to belabor sort of all the things that are wrong, but I think it's important to understand sort of the conceptual level all of these things and recognizing now the system is functionally broken and the way we apply it is more broken. And so wanting to think about what can we do to go through and change things. And again, not laying it on you all to be the revolution, start the revolution and change everything, but sort of at least making you aware and sort of trying to provide things that might be additional alternatives that we can incorporate relatively easily within the context of things. And sorry to move 5 minutes. I think this. I mean, it's like so I'm up here like sort of giving, talking about the millionaires, the billionaires, and it's like. It's important stuff, though, and part of the reason we continue to perpetuate this stuff is because we don't spend enough time talking about it and thinking about it carefully as we're going through and interpreting our data. And so, at least for this next 2 semesters, I'm going to try and give you guys tools and language to start thinking about things carefully, and then if you decide to disregard it, so that's fine. Okay, so thinking about, so we talked about why this is such an issue, but people have been talking about this since the 40s, right? But like any behavior, it persists for a reason, right? Behaviors don't just persist for no reason at all, right? There's got to be something that continues to motivate it, right? And one thing that p-values do is they give us a reasonable set of communications, right? If I'm going through and CJ has run a study using these methods, and I run a study using different methods, that p-value is a common sort of language, right? I know sort of based on our standard threshold, sort of what it means if it's above or below, and so I've done something. This is one of the things that makes effect sizes difficult, because depending on what tests you're running, there's different effect sizes for different tests and things like that, and it starts to get complicated. A P is a P is a P is a P is a P, right? And it makes it easy and convenient to go through and take a look and evaluate things, right? Our p-value, or sort of test, we've got this bright line at 0.05. It also gives us an easy decision criteria, right? Alicia found something that fell below p, or fell above p 0.05. So we're saying, for better or for worse, we're saying that's not important. Tomorrow found something p less than 0.05. We're saying okay. It helps us give us sort of a line between sort of what are we going to take seriously and what are we not. Now the problem is that bright line created a bright line, an arbitrary line, sort of in a continuum of evidence that we just said, oh, everything here is great, we're going to interpret this as a real effect, and everything under it is sort of not worth looking at or inconclusive. But again, we like bright line criteria. Like, this is the thing I fight with you guys not you guys, but sort of first year graduate students. How do I make the decision? Well, how do I say whether or not it's problematic or not, right? And we gravitate to sort of rules of thumb and things like that. The problem is that those often will lead us astray, will lead us into making bad decisions, but they're easy when we like it, right? So this whole system is what we teach and what we learn and what we use. It sort of perpetuates that. We don't have good consensus on a better way to do things, right? This is the hard thing. We've got different ideas and recommendations, but no one to date has come up and said, this is a clearly better way to go through and analyze data that doesn't involve this system, that is free of all sort of the limitations and sort of has no additional costs. We don't have that yet. We've got sort of the closest thing we've got is Bayesian types of analyses, but they come with their own baggage and things like that that make it, in many cases, infeasible, right? And so we're kind of stuck with it. And then finally, this is our currency, right? Like, this is what gets you published or not published, right? Say I'm an NBA coach and I decide that I don't think certain rules of the game are great, so I decide to do something different. Well, that's fine, but you still got to play by the rules, right? I mean, cool, dude, but whatever. Like, these are the rules of the game. Like, if you don't play by the rules, you're going to suffer the consequences. And this is what ends up happening too. Is it's hard to go through and change if I'm going to have people reviewing papers and this is what they're expecting to see. And if I just start flying off the radar with other stuff that people don't understand, and I haven't communicated effectively how to go through and interpret it, it's possible that there could be costs for that, right? And so, again, thinking about sort of null hypothesis testing is sort of valued in terms of the same reason we value money. I think is a nice example of kind of what's going on with this stuff. So, things that we agree on, okay? We've got, sort of from a methodological standpoint, even for people who are sort of very much invested in our current system of analyses, we generally agree on some basic things, right? that we should probably pay more attention to precision of our estimates, right? Again, to the arguments that precision is at the heart of what we do. This idea that if we're gonna do things and sort of run our analysis, we should pay closer attention to how precise, how confident could we be. So I've said the point estimate, my best estimate of the point estimate of the population is X. So how much wiggle room do I have on that? How much confidence, how precise do I expect my estimate to be? And so there's interval estimates can help us out with this. Magnitude of effect, we've got effect sizes. So not just is it different than 0, how much is it different than 0? Thinking about that. Always placing context, placing research and results into the context of existing knowledge. It drives me nuts when I'm just going to go through and trying to read something. Someone talks about their study, so it's reviewing manuscripts, right? For publication, not my students, other people. Like, oh, this is what we found, this is what we found, this is what we found. Like, well, tell me what other people have found. Like, how does this relate to sort of all the work that's been done in this area? And not just, is it significant or not significant? How does this fit? What does this help? How does this move things, right? Interpreting studies in isolation is bad business. Evaluating our methodology, we talked about this, right? We can't sort of draw meaningful conclusions about anything unless we know how we would obtain these data, and then recognizing the limitations of our framework. Again, knowing that our whole system of science is based on the assumption of a best case scenario. I ran a perfect study with no violations. So at best, this is an upper bound of what I could expect. In actual fact, so the addition of stuff probably starts to degrade this quite a bit. Okay. So what do? A lot of strong suggestions and things that have been recommended, and there's disagreement on sort of what people think is a good idea and things that people have criticized, think maybe not a great idea. One thing that is pretty consistent, this idea to report exact p-values, okay? Again, we've talked about p-values, p-value as a measure of compatibility between the null hypotheses and the observed data, bounded by 0, which is complete incompatibility. My p-value is 0, right? These data are entirely inconsistent with the null and the corresponding assumptions. Functionally, these data can't have occurred if this null hypothesis is true. All the way to 1, no incompatibility apparent from the test. Like, these data are exactly what we would expect if the null hypothesis and corresponding assumptions of the statistical model were true. This asterisk here saying that this is something we're going to continue doing. I don't know, man, I'm going to start playing around with this, because what we do not, under any circumstances, give me something that says p less than 0.05 or less than or equal to 0.05, things along those lines. That's not useful, okay? Our convention within psychological science is to report to 3 values, right? But if we start to think about this, and we start to think about p as an indication of continuous evidence against the null hypothesis and corresponding assumptions, are those two things equivalent? No, right? And so it starts to become sort of difficult in terms of thinking. So what we generally do for both of these, we would say p less than 0.001. And that's convention, and that's typically what we do, and that's fine, right? But as I've been starting to think about sort of looking at these best practice recommendations, right? And sort of the implications for our science and how we do things, it sort of starts to make sense to start thinking about, well, sort of this is intensely more evidence against the null than this. They're both evidence against it, fairly strong evidence against it, but this is kind of at a whole different level than this, right? And so the possibility of thinking about, say, p equals 2.35 to the negative 5. Oops, not that. Okay. The possibility of using scientific notation to really communicate sort of like to the actual value of this, right? Who's familiar with scientific notation? Anybody? Yeah, so it's going through moving that decimal, right? So this actually saying P equals 0.0000235. Okay, so it's -5, so we just move that decimal place 1, 2, 3, 4, 5 places, right? But thinking about ways we can start to communicate to the actual p-value, if we're thinking about p-values as literally an as a measure of evidence against the null hypotheses, man, I could do this, but if this is really what my test found, I might even want to communicate that in a way that's more efficient to people. So again, I don't know. I'm thinking about trying to incorporate this in my own research, and so we'll see. I'll let you know how it goes. People might really stop being friggin' weird and just step in line. But I mean, if we're thinking about this literally as an index of the evidence against the null, assuming the model, then these two things start to become sort of not similar, right? So at the very least, reporting this and not just saying p less than 0.05. So reporting p-values precisely. As I talked about before, another suggestion has been to increase the threshold for statistical significance. Say for a novel discovery, for something that's never been found before, or it's a completely new thing, say in order to call it statistically significant, it has to be p less than or equal to 0.005. Anything between 0.05 and 0.005, qualifying that as suggestive, right? The problem with this is sort of potential for this to hypercharge sort of the overestimation of effects in our literature, right? And again, incentivize people for gaming the system to cherry pick responses and start doing weird stuff with their data to then go through whatever bright line decision that we make in terms of what meets criteria for publication. People are going to there's potential for shenanigans going on in that stuff. And so in general, this is a suggestion, but sort of a lot of methodologists are saying this sort of just exacerbates the problem, actually doesn't make it better. But one thing that people have made an argument for is augmenting interval estimates and statistical tests with something called S-values, okay? We'll talk about this in the next set of slides, but basically you can get an S-value directly from your p-value. It's a nonlinear transform of p. And the idea is that, the problem is that p is not a great, the metric isn't great, right? The difference between 0.99 and 0.90 in terms of a p-value is not the same level of evidence against the null hypotheses as p equals 0.01 and p 0.001, right? And so what this S-value does with this nonlinear, or this log 2-based transform, what you would do is calculate the p, or sort of calculate your S-value, round your S-value to the nearest integer, and then interpret that S-value as evidence against the null, interpreted as plausibility of a fair coin being called consecutively times heads, right? So if we go through and we'll do this S-value for p equals 0.05, S-value ends up being 4, okay? And so what we would do is we would say, essentially, I give you a coin, and I say, hey, this is a fair coin, and I flip it and it's heads, 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 right? 4 times in a row. How much evidence are you reading into that as evidence against that this is a fair coin? I'm starting to get suspicious, right? But could I get 4 heads in a row? Yeah, I could, right? But identifying sort of this, and this is our threshold for what we're calling statistically significant, but within this S-value, so thinking about this as a better estimate for sort of gauging the evidence against the null hypotheses. And so surprisingly, I mean, it's not likely. I'd start to get suspicious, but I don't know if I'd say at that point 100%, yeah, this isn't a fair coin, right? The nice thing I like about this S-value is it's something that you can calculate just from the P that you're already getting. And this kind of makes it an attractive thing to start to incorporate that doesn't go through and disrupt our whole system with knowing. Other thing too, another example, sort of using p-value, augmenting our tests with the database odds of the alternative to the null. And this is kind of intriguing. This is starting to incorporate some Bayesian types of thinking. Basically what we're doing is we're calculating something called a Bayes factor bound based on, again, a nonlinear transform of our p-value that we're already getting, and interpreting this as evidence for the ratio as the strongest case for the alternative hypotheses relative to the null hypothesis. Anybody here work with sort of odds ratios or odds in their work, doing categorical logistic stuff? Basically what it's saying, sort of, anybody like hardcore sports betting? Sort of deep in the hole in your bookie because you don't understand odds correctly? Okay. So basically what we're saying, the odds of the null, or odds of the alternative relative to the null, right? So maybe my Bayes factor bound is 5.1, right? And what it's going to say is basically I'm saying this is giving me, in the best case scenario, right? This is giving me the strongest case for the odds of the alternative relative to the null. I'm saying that the alternative is about 5 times more likely than the null based on the data that I've collected. And this also has some intuitive meaning to it, right? And starting to say, okay, that means something to me. And so if something is 5 times more likely than something else, is that possible? No, but I don't know, that's, if you gave me 5 to 1 odds on some bet, I'll take it, right? Particularly if it's even money, right? And so starting again to use the stuff that we're already getting from our statistical output to go through and just with this quick calculation that we'll set up a calculator for, starting to add some interpretation there. Other recommendations, looking at things that start to look at interval null stuff. So this idea that whether or not something is exactly equal to 0 is not meaningful or interesting, right? And starting to incorporate what we start to talk about is, or what's sometimes called a thick null. So instead of a point null, where the null is exactly 0, I'm saying my null interval range is anywhere from -5 to +5, right? And then basically running a series of statistical tests that if my confidence, then I'm concluding that this is not only statistically significant, but also practically meaningful. If the lower bound of my estimate is considerably above sort of the bounds for what I would consider practically meaningful, this being stronger evidence in terms of looking at things in terms of something that's statistically large enough to make some sense for me to do. Now the problem is, I really like this, but this requires an intensive knowledge of your area to be able to determine what constitutes a meaningful effect. And a lot of the stuff we do is theory-based stuff. My theory says that sort of these two things should be different, or that this effect should take place. Now, for me to tack down exactly how big that would have to be in order for me to be interested in it, that's a pretty high burden. And so something that we're probably not going to incorporate, and it's a whole different procedure, but this is kind of the idea behind minimum practically significant difference. So also some similar types of recommendations for what have been called second generation p-values. What we're doing is again taking this interval null and looking at what proportion of the alternate hypotheses are practically null, right? So, for example, scenario 1, right, in the antioxidant thing, low end was like 84, high end was 100, right? If I say that there's a difference of 10, that means so what proportion of point estimates or population estimates within that interval contain a difference of 10 or more, and then using that as, based on my analysis, what proportion of the alternative hypotheses that are suggested in my data are consistent with stuff that are scientifically null or practically null, right? But again, that requires some ability to say, so these are the levels, or these are the values around the point null that are practically meaningful. And then some different stuff, we're talking about ANCRED, looking at, this is what I've found. How much weight, how much evidence would I need from the existing literature in order to nullify this effect or provide support for this effect? This is a little bit more complex, but interesting, starting to incorporate, this is what I've found. How does this relate to existing evidence, and how big of effects would I need to be seeing in the stuff that's already available in order for me to place confidence in this is a credible effect? These things are very, very interesting, but involve a whole different procedure. Your advisors will probably jump me if I try to go through and suggest that you learn a completely different approach to or sort of scientific investigation than sort of what's common among our practice. It wouldn't be sort of fair to you to say, all right, we're going to do something completely different that no one else understands. That's not going to sort of play into anything that you will do for your own research. But these two things, so the base factor, boundary, S values, we're going to play around with incorporating those and see what we can do, and so that seeing the extent to which that helps us maybe qualify some of our effects a little bit better. Okay. That's fine. I can put that on there, right? Like that's right. You back up to super excited about it. I'm getting that I can. So for next year, tell people don't be scientifically thirsty. Right? That seems fine. All right. We're doing really good. We're kind of on time in terms of stuff. It took us a little bit longer to work through some of this stuff today, but we'll get into t-tests and sort of mean-based comparisons on Wednesday. This is where we'll go through, we'll start working with SPSS and sort of output and things along those lines. We'll do some demonstrations and get you in the mix of that. I'll go through and post up problem set 3, which will be based on this the stuff we've got here. So again, just work on that. We won't be working with sort of actual data sets or things like that, but just make sure that you're giving yourself enough time to go through and get all that stuff put together. And if you have any questions, make sure that you're coming through touching base with us. We'll get you scored away. Sound good? Cool. All right. Thanks, everyone.